So in continuation to the previous discussion on the diode voltage operation, and then the forward bias and the reverse bias conditions, we will talk further. Previously we have clearly mentioned that diode is basically used in most of the applications where a reverse blocking is required. That means the diode conducts, as mentioned here, the diode conducts in one side and blocks on the other side. When we are talking about a generic diode here, but in the industry, if you see, there are many diodes that are there and which are used in many electrical applications. So to name a few, the light emitting diode, Gina diode, Schottky, avalanche, and pin diode. So how is it different from the normal diode? So the previous characteristics that we have discussed and the one that is shown here are basically the characteristics of the normal diode. So the composition and the materials that are used for the other diodes like light emitting, Zener, Schottky and all are totally different from the normal diode. So we will discuss about them when we proceed further into the depth of these devices. Right now we will restrict our discussion around the normal diode. So if you see here, this is called the characteristic curve of the diode. So what does the characteristic curve represent? The characteristic curve represents the amount of current that is passing through a diode when a voltage X is applied. So now when you apply that voltage beyond a certain limit, the diode breaks down and starts conducting. This condition is called the forward bias condition. So now how much voltage can I apply to the diode is like determined by this breakdown voltage. So now let us assume a diode's breakdown voltage is 0.6 volt. Now when I apply 0.6 volt, the diode starts conducting. If I go on increasing the voltage, the actual current increases exponentially. So in the next slide we will see the equation which shows the exponential increase in the current. So based on that we can determine the amount of current that is passing. So it is not good to apply more voltage than the desired breakdown, or a voltage around the breakdown to be applied. And if you go on applying the voltage to higher voltage to the diode breaks down and the charge carriers flow so intensely the diode breaks down, and it may fail at some extent. So we will discuss this again. And then when it comes to reverse bias, it is the similar way in the forward bias. You can see a sharp increase in the current. So if you apply a voltage beyond a limit in the reverse bias condition, the same thing that we have described in the forward bias condition happens, but in the reverse bias conditions it is more dangerous. So this is how a diode voltage operation is described. Now when you come here, so you can see here we have described about the majority and minority carriers when we have discussed about the semiconductors. So in reverse bias condition, the condition you see here, the major current, we discussed that there is no conduction, but there is very little conduction, which is called the reverse saturation current. So that amount of current will flow through which is very minimal, and it is in microamps or nanoamps. So in the diode data sheets you can see these values. Now when it comes to forward, generally the diode forward drop is 0.3 volt with germanium and 0.7 volts with silicon. So these are the standard values for the germanium and silicon diodes. Now there is, as we have discussed in the previous slide, there is an equation which determines the amount of current that flows in the forward bias. So this is the equation. And then you see the picture here. This is the actual picture of the diode in reality. So this terminal where you see a small band, this is called the cathode, and the other side is the anode. So based on this you can clearly identify what is the anode and cathode of the diode.